On the asteroid, Bennu scientists found RNA building blocks where radiation should have erased them. To the naked eye, Bennu looks like nothing more than a drifting pile of rubble, a hazardous debris field left over from the dawn of the solar system. But NASA didn't spend 7 years and over $1 billion to collect rocks. This mission was designed to retrieve specific chemical clues about the origin of life. What OSIRIS-REx brought back defies the harsh logic of space-fragile sugars and RNA components, the molecular architecture of biology surviving in a radioactive vacuum that should have destroyed them billions of years ago. How does something so delicate exist in a place so hostile? To answer that, we have to follow the evidence through fire failure and the narrowest margins of survival. On September 24, 2023, the silence of the Utah desert was broken, not by an impact, but by a return. High above the Department of Defense's testing range, the sky was torn apart by a streak of fire moving at 43,000 kilometers per hour. This was the OSIRIS-REx sample return capsule, screaming through the atmosphere at speeds that turned the air around it into plasma. Minutes later, the violence of re-entry gave way to a parachute's gentle bloom. The capsule touched down on the scorched earth, a small charred cone resting in the middle of nowhere. Helicopters descended immediately. Men and women in full-body hazmat suits swarmed the landing site, moving with the precision of a high-risk recovery team. But they weren't there to contain a virus or defuse an explosive. Their mission was reversed. They were protecting the capsule from Earth. Inside that heat-shielded fortress lay the Utah paradox, a sample of the primordial solar system, pristine and untouched for 5 billion years now, resting on a planet teeming with biological noise. The recovery team had to secure the site before a single breath of Earth's air could corrupt the sample. This blackened canister carried chemical evidence tracing back to our origins. But for this peaceful landing to happen, a robotic explorer first had to survive a 7-year journey through gravity radiation and near failure in deep space. To understand what this sample truly represents, we have to rewind the clock and follow the evidence back to its source. When OSIRIS-REx finally caught up with its target in December 2018, the navigational radar maps generated from Earth immediately became obsolete. The mission planners had spent years studying thermal models and radar echoes, predicting that Bennu would be a relatively smooth body, a beach-like world covered in fine-grained sand, ideal for a touch-and-go sample grab. What the spacecraft's cameras revealed instead was a surface far more hostile than predicted. Bennu wasn't a solid monolith. It was a rubble pile, a loose aggregation of rocks and debris held together by gravity so weak it was barely functional. From orbit, it looked less like a planetoid and more like a construction site suspended in the void. Massive boulders, some the size of parking garages, littered the surface, leaving almost no open space for the spacecraft to descend. But the chaotic terrain was only the surface expression. The underlying cause was the asteroid's own physics. Deep dive analysis revealed that Bennu is a dynamic, evolving system, slowly tearing itself apart. The driving mechanism is the Yorpy effect, a phenomenon where sunlight heating the uneven surface creates a tiny but persistent thermal push. Over millions of years, this pressure has spun Bennu up like a top. The asteroid rotates once every 4.3 hours a speed that pushes its structural integrity to the limit. In fact, Bennu is spinning so fast that at its equator, centrifugal force nearly cancels out gravity. Rocks aren't just sitting there, they are drifting, sometimes lifting off entirely in particle ejection events, casting debris into orbit before slamming back down. This wasn't a stable landing ground. It was a fracturing centrifuge flinging its contents into the dark. We weren't trying to land on an island. We were trying to park a billion-dollar vehicle on a landslide that was happening in slow motion. The mission parameters were clear: find a hazard-free circle of fine regolith, at least 50 meters in diameter, to ensure the safety of the spacecraft. After scanning the entire surface, the team came to a chilling realization. A 50-meter site did not exist. There wasn't even a 20-meter site. The mission faced a abort or adapt crisis. The navigation software designed for a wide margin of error had to be rewritten mid-flight to target a bullseye much smaller than originally planned. The search for a landing zone became a hunt for the least hazardous option. They narrowed it down to 4 sites, birds of prey, named Osprey, Kingfisher, Sandpiper, and the final choice, Nightingale. Nightingale was a crater located high in Bennu's northern hemisphere. It offered the freshest material regolith that hadn't been baked by the sun for eons, but the cost of entry was exorbitant. The safe zone was only 16 meters wide, roughly the size of a few parking spaces surrounded by Mount Doom, a perimeter of jagged boulders the size of buildings. To make matters worse, OSIRIS-REx would have to perform the descent autonomously. At a distance of nearly 300 million kilometers, radio signals took over 18 minutes to travel one way. Real-time joystick control was impossible. The spacecraft had to use natural feature tracking, comparing what it saw in real time against a catalog of onboard hazard maps. It had to think for itself. If it drifted just a few meters off course, it wouldn't just fail the mission. It would be sheared apart by the crater walls before Earth even received the descent started signal. On October 20th, 2020, the command was locked in. OSIRIS-REx began its slow, perilous fall toward the Nightingale crater. The computer was flying blind, guiding a delicate instrument into an environment with no margin for error. The countdown to contact was measured in centimeters. OSIRIS-REx extended its robotic arm, the touch-and-go sample acquisition mechanism, forward. The plan was simple and mechanical: tap the surface, gently fire a burst of nitrogen gas to stir up some dust, catch the debris in the filter, and bounce off immediately like a pogo stick. The engineers called it a touch-and-go. But on Bennu, the laws of interaction are not written in stone. They are written in powder. At the moment of impact, the sensors did not register the sharp resistance of a solid surface. Instead, they recorded an absence of friction. The spacecraft didn't bounce. It plunged. In the microgravity environment of Bennu, where the gravitational pull is mere millionths of Earth's, the surface material possesses a deceptive quality known as granular fluidity. Without strong gravity to compress them, the rocks and dust particles are held together only by the ghostly grip of van der Waals forces, weak electrostatic attractions between molecules. It is a cohesionless state. To the eye, it looks like a rocky floor. To a physical object striking it, it acts like a viscous fluid. OSIRIS-REx wasn't landing on a parking lot. It was stepping into a bottomless ball pit. The sampling head punched through the outer crust with zero resistance, sinking nearly half a meter into the asteroid's body. For a few heart-stopping seconds, the billion-dollar explorer was being swallowed by the surface. The rocks flowed around the mechanism, threatening to engulf the thrusters and permanently anchor the spacecraft to the surface. Then the automated sequence kicked in. The nitrogen gas bottle fired. On Earth, a blast of gas might kick up a dust cloud. In the vacuum and microgravity of Bennu, it was a seismic event. The gas expansion didn't just stir the regolith, it fluidized the entire impact zone. The blast displaced 6 tons of rock, creating a massive crater and launching a wall of debris into space. The spacecraft, sensing the chaotic deceleration and the drag of the fluidized regolith, fired its backaway thrusters with maximum authority. OSIRIS-REx tore itself free from the granular trap, leaving behind a scarred surface that would never look the same again. It had survived the encounter, but the violence of the extraction had consequences that no simulation could have predicted. Safe in orbit, the mission team commanded the spacecraft to turn its cameras toward the sample head to verify the catch. The images that beamed back to Earth turned celebration into immediate dread. The collector was overflowing. The collection had exceeded its design limits. The sampling head was designed to catch 60 grams of material. It had grabbed hundreds, perhaps a kilogram or more. But in the violence of the nitrogen blast and the fluidic sinking, large rocks had been forced into the mechanism. The mylar flap designed to snap shut and seal the sample inside was jammed open. A wedge of rock acting like a foot in a door prevented the seal from closing. Through the gap, the precious cargo was escaping. The camera captured a mesmerizing but horrifying scene. Particles of the primordial solar system were drifting out of the collector, floating away into the black void like dandelion seeds in a breeze. This was a bleeding of evidence. Every time the spacecraft fired its thrusters to correct its orientation, the slight jolt shook more material loose. The mission had successfully secured the most valuable chemical record in history, only to watch it slowly evaporate. The original flight plan called for a spin maneuver, spinning the spacecraft to measure the mass of the sample by the change in inertia. That plan was immediately scrapped. Spinning the ship now would act like a centrifuge, flinging the remaining sample out into space. The priority shifted from measure to stow. The team had to race against the physics of momentum. They initiated an emergency stowage procedure guiding the leaking head into the return capsule years ahead of schedule. It was a delicate operation performed with a do-no-harm mandate: move too fast, and you lose the sample. Move too slow, and you lose the sample. Finally, the collector was locked into the sample return capsule. The door was bolted shut. The leak was stopped. OSIRIS-REx had secured the sample, but the integrity of the chain of custody had faced its first major test. The sample was safe from the vacuum, but now it had to survive the journey home. The spacecraft turned its back on the asteroid and aimed its high-gain antenna toward the blue marble in the distance. The thermal gauntlet awaited. On September 24, 2023, the sample return capsule separated from the mothership and oriented itself toward Earth. The physical extraction from Bennu was dangerous, but it was a slow-motion struggle. What came next was a ballistic phase with no margin for error. The next threat to the chain of custody wasn't the freezing vacuum or the microgravity of deep space. It was the atmosphere of the very planet eager to receive it. To bring the sample home, the capsule had to execute a precisely calculated atmospheric entry. It hit the upper atmosphere at 12.3 kilometers per second, roughly 43,000 kilometers per hour. That is 15 times faster than a rifle bullet. At this hypersonic speed, the air ahead of the capsule cannot move out of the way fast enough. It gets trapped and compressed violently against the blunt face of the heat shield. In physics, extreme compression equals extreme heat. The air molecules are crushed until they are stripped of their electrons, turning into a glowing sheath of plasma. This wasn't just a hot ride, it was a thermal wall. The temperature on the nose of the capsule spiked to 2,760 degrees Celsius, half the temperature of the surface of the sun. Inside, the canister separated from this extreme thermal environment. By only a few inches of material sat the prizes: fragile organic molecules, hydrated clays, and the elusive sugars of life. These compounds are chemically temperamental. If the internal temperature rose above 75 degrees Celsius, the temperature of a hot cup of coffee, the chemical bonds of the ribose would break down. The chemical evidence we had traveled 2 billion kilometers to collect would be erased by the heat of our own front door. To solve this thermodynamic paradox, NASA engineers wrapped the capsule in a material called pica, short for phenolic impregnated carbon ablator. It is a technology that operates on the principle of sacrifice. Pica is not designed to withstand the heat indefinitely. It is designed to ablate so the payload remains protected. As the plasma shockwave licks the surface, the shield undergoes pyrolysis. It chars, melts, and vaporizes. This process, known as ablation, is a masterstroke of physics. As the solid material turns into gas, it carries the heat energy away from the capsule, creating a boundary layer of cooler gas that acts as a buffer. The shield literally peels itself away atom by atom, gradually receding to maintain a survivable internal temperature. For 2 agonizing minutes, the capsule was a falling meteor, enduring a deceleration force of 32 Gs. To put that in perspective, a trained fighter pilot might lose consciousness at 9 Gs. At 32 Gs, the structural integrity of the canister was being crushed by 32 times its own weight. Every bolt, every seal, every weld was tested to its breaking point. If the shield had a microfracture or if the angle of entry had been too steep, the heat would have breached the interior. The organic evidence would have been pyrolyzed, rendered chemically unusable. The mission would have ended not with a scientific breakthrough, but with a sterile rock in a burnt box. But the math held. The pica shield sacrificed itself perfectly. The parachutes bloomed. The capsule slowed from hypersonic velocity to a gentle 18 kilometers per hour, touching down on the Utah desert floor. The physical journey was over. The violence of space travel had ended. Now a different kind of rigor was required, the pristine, obsessive silence of the clean room. The capsule had survived the void, the reentry fire, and the Utah impact. Now it faced its final and perhaps most difficult journey, the few meters from the transport container into the pristine isolation of the curation lab at NASA's Johnson Space Center in Houston. Here, the primary threat was no longer gravity or heat, but biological contamination. Every breath we exhale, every flake of skin we shed, is a biological contaminant. If a single microbe from a technician's glove were to touch the sample, it would compromise the interpretability of a 4.5 billion-year-old record. The chain of custody demanded an environment cleaner than a surgical operating theater. The sample was moved into a custom-built glove box, not filled with air, but constantly purged with pure nitrogen gas. Nitrogen is inert. It doesn't react, it doesn't oxidize, and most importantly, it suppresses the biology of Earth. But just when the scientists prepared to access the main treasure, the bulk sample inside the TAGSAM head, the mission hit a baffling low-tech wall. The canister refused to open. 2 of the 35 high-strength fasteners sealing the lid were stuck. The culprits were tiny grains of Bennu's dust. During the violent collection event years prior, the pervasive grit had worked its way into the threads of the screws. In the vacuum of space, metals can undergo a process called cold welding, and combined with the friction of the dust, the fasteners were seized solid. It was a cruel irony. A billion-dollar spacecraft had successfully navigated the solar system only to be defeated by 2 stuck screws. The team could not simply grab a drill or spray some WD-40. Lubricants are contaminants. Drills create metal shavings and heat, which would cook the delicate organics inside. The forensic deconstruction ground to a halt. For 3.5 months, the curation team had to design and fabricate entirely new tools made from a specific grade of surgical non-magnetic stainless steel just to perform this delicate extraction. It was a slow, highly constrained extraction process performed through thick rubber gloves, testing the patience of the scientific world. Finally, on January 11, 2024, the torque was applied. The fasteners gave way. The lid was lifted. The interior was revealed. The dust inside was dark, fine, and abundant, 121.6 grams of material, double the mission's goal. But quantity is irrelevant if the quality doesn't hold up. As the spectrometers began to dissect the sample atom by atom, the chemical verdict began to take shape, and the results required careful interpretation. First, the context. The sample was rich in hydrated clay minerals. This confirmed that Bennu, now a dry rock, was once part of a much larger water-rich parent body, an ancient ocean world that likely shattered billions of years ago. But the headlines belonged to the organics. The team found carbon. They found nitrogen. They found uracil, one of the 4 essential nucleobases of RNA. These are the letters of the genetic alphabet. But the most chemically significant finding was the detection of ribose, Ribose is a sugar. It is the R in RNA ribonucleic acid. Its discovery in a pristine asteroid sample is chemically counterintuitive. Sugars are fragile molecules. In water, they break down. In heat, they rapidly degrade into chemically uninformative residues. In the harsh radiation of space, they should have been destroyed eons ago. This is known as the sugar paradox. How did it survive? The answer lay in another trace element found alongside it, boron. Dr. Stephen Benner and the analysis team identified that the ribose wasn't just floating free, it was likely stabilized by borate minerals. In a remarkable feat of prebiotic chemistry, boron acts as a chemical clamp, or a preservative. It binds to the sugar molecule, locking its structure in place and shielding it from degradation. This discovery changes the narrative. It suggests that asteroids like Bennu aren't just dumb rocks transporting random debris. They host chemical environments capable of selective synthesis and preservation. They possess the specific mineralogical conditions, the stabilizing agents necessary to manufacture and preserve the building blocks of life. Critically, the analysis did not find deoxyribose, the sugar that forms DNA. The presence of the RNA sugar without the DNA sugar provides powerful inferential evidence for the RNA World hypothesis, the idea that biology began with RNA before evolving into the complex DNA life we see today. The evidence from Bennu does not support the claim that life came from space. That is a leap too far. The verdict is that the supply chain for life is cosmic. The bricks uracil, the mortar ribose, and the protective packaging boron were all manufactured in the dark billions of years before the first cell divided on Earth. We have found the hardware. The mystery that remains is how and where the software was installed. The OSIRIS-REx mission has officially ended, but the scientific analysis of the Bennu samples has only just begun. What sits in the curation vaults of Houston is not just a pile of black dust. It is a chemical record dating back to the solar nebula. For decades, we have looked at the asteroid belt as a graveyard, a collection of dry, dead rocks drifting aimlessly in the dark. The Bennu dossier forces us to rewrite that profile. These objects are not dead. They are dormant. They are geochemically active vessels that have been storing, protecting, and transporting the delicate machinery of biology for billions of years. However, a distinction must be made. The forensic evidence does not prove that life originated in space. We have found the ingredients, not the meal. We have found the bricks, not the cathedral. Finding ribose and uracil is like finding a hard drive and a power cable. It does not guarantee that the operating system is installed. Yet the implications are profound. The presence of boron-stabilized sugars suggests that the universe has a chemical bias. It implies that the formation of life's building blocks is not a miraculous accident restricted to Earth, but a repeatable chemical pathway that may occur on many rocky bodies across the solar system. This suggests the existence of a widespread prebiotic distribution network. If Bennu delivered these materials to Earth during the late heavy bombardment, it likely delivered them to Mars, to Venus, and to any other world willing to receive the shipment. In the end, the paradox of the Utah desert is resolved. We opened the black box expecting to find something alien. Instead, we found something hauntingly familiar. In those grains of carbon and sugar, we are looking at a snapshot of ourselves before we existed. The detective story of our origins is far from solved. There are still missing pages. But, thanks to a robotic detective that braved the granular traps and thermal firestorms of the void, we now know exactly where to look for the rest of the manuscript. The evidence suggests that the raw materials for life were present long before life itself emerged.